So what I want to do next is to try to connect the logistic regression with Bayesian decision rule, and afterwards I want to show you some connections with the linear regressions. So let's first talk about the Bayesian decision rule. Okay, so by far we should be able to analyze a Bayesian decision rule because we know how it is being formulated. It has certain connections with the linear regression, and to study the linear regression, we know that we just need to make some assumptions of the Gaussian model. So we are going to do the same thing here. We're going to make some assumptions on the Gaussian model, and then we want to see under these conditions, then the logistic and also the Bayesian decision rule, they becomes the same. Okay, so let's start with a Gaussian model. So you have this likelihood function, and then you have a prior, so you have two classes. Now, I am going to consider the posterior probability, because last time when we introduced logistic regression, we mentioned that logistic regression has a very interesting form, being the posterior probability. And so we want to analyze the posterior probability of this Gaussian distribution and see if we are able to connect back to the logistic case. If you look at the posterior distribution of this Gaussian random variable, you realize that the posterior is given by a ratio. This is given by the Bayes theorem. You have a likelihood of x given 1, and then y of 1, and then in the denominator you have the sum of these two cases. So that's the Bayes theorem. And now I can do a simple trick. I am going to divide the numerator and also the denominator by the likelihood times the prior. And so what I'm going to do is that I'm going to divide this by p of x given 1 and then p of 1, and then this entire denominator I will do the same thing. Okay, and then you can group the terms together. You will be able to see this new ratio of 1 over 1 plus this ratio between the 0th case and then the 1th case. Then I'm going to do a very nonsense trick. I'm going to put a log here, and then I'm going to put an exponential here. Okay, of course these two will cancel out each other. And then I'm also putting a negative sign here because I'm flipping the denominator and also the numerator. Okay, now once I do that, then you can see that this is taking a log on a ratio. And in this ratio, in the numerator, there are two terms. Denominator, you have two terms. And that means I can pull out this pair of numbers and then put it out. Okay, so you have minus log of this pi 1 divided by pi 0. Okay, because py of 1 is pi 1, py of 0 is pi 0. So you have this term. And then you have minus log of this ratio, p of case 1, p of case 0. Okay, so I have written my posterior into this very, very strange form, and I want to do some magic here. The magic that I'm going to do is to look at this gigantic term. I'm going to just focus on this log of the ratio. This log of the ratio is what? This is the log of the likelihood terms, and since I know that the likelihood is Gaussian, I can just put a Gaussian likelihood into the numerator and also the denominator. Then you see something interesting. First of all, this is a constant for both, and so you can cancel them out. And second, there is exponential in both the numerator and denominator. So that means you can group the terms together. Okay, it becomes exponential of this minus that. And since you have a log outside, these exponentials will go away. And therefore, you will left with this minus 1/2 of the numerator, that's a Mahalanobis distance, minus the other distance. Okay? And so then what? Well, then you can start to group the terms together by realizing that here you have x sigma inverse x. Here you also have x sigma inverse x. So that means the quadratic term in this expression, they cancel out, because you have a minus here. Now, what's remaining is the linear term that involves your x, and also the constant term that involves mu1 and mu0. Okay, so when you group the terms together, you can show that this log of the ratio of the likelihood will give you a linear term that contains mu1 minus mu0 transpose sigma inverse. And then you have a constant term that doesn't involve any x. This term should get familiar because if we are thinking about the Bayesian decision rule, we realize that this is really the vector that points from class 1 to class 0, and that is the traveling direction from the class. And so the normal to this vector will be your separating hyperplane, right? So everything comes back when you see this expression. So now what I'm going to do is that I'm going to define this as my W vector. Okay, so go to here. So this is W vector. And then I'm going to define this constant as my W0. Then you realize that there's also a log that should be that is not present in this term, because there's a log of pi 1 divided by pi 0 that comes from here, right? So you have a sum of these two terms. And therefore you have this log of the likelihood ratio, and you show that you can write it in terms of a very interesting form, which is that go back to this slide. This entire thing can become W transpose X plus W0. There's a minus sign outside. Okay, so that is the connection. So what? Well, so now you look at this log of the likelihood ratio, and then it can be written as this W transpose X plus W0, and then this should be okay. All right, so because this is log of the likelihood ratio, and so that you should have this log of the this pi 1 and pi 0 there, and then eventually you can show that this posterior probability is given by 1 divided by 1 plus exponential of minus W transpose X plus W0. Now, what is this term? This term is exactly equal to your sigmoid of W transpose X plus W0. This is logistic regression. Okay? Here it shows that this is the posterior probability of a Gaussian distribution that comes from the Bayesian decision rule. This derivation shows you that the sigmoid function on this linear discriminant function is the posterior, and therefore you can see the linkage between the two methods. When you do logistic regression, the logistic regression function that you're getting has a posterior perspective. It can be regarded as a posterior distribution of a Gaussian random variable in the Bayesian decision rule setting. Okay? Now, if you go away from the Gaussian case, then you may lose this perspective. Okay? It is still, you can still treat it like a posterior distribution, but you just don't know what kind of posterior distribution it is. Okay? So if you put it into this way, then what I can say is that if the underlying distribution is Gaussian, then my sigmoid function is indeed the posterior of that true Gaussian. If my underlying distribution is not Gaussian, it's going to calculate something. It has certain interpretation like the posterior of a Gaussian, but it's not the posterior of a Gaussian. See the difference? Okay. So you need to know whether your underlying distribution is indeed a Gaussian. If it's indeed a Gaussian, furthermore, you need to make assumption about your Gaussian. What is the assumption? The assumption you're making is that they both have the same sigma. If they have different sigmas, then it's no longer a linear classifier. You need to use a quadratic classifier, and by construction, your logistic regression is a first order thing. You cannot handle the second order behavior. Okay, so that gives you the connection between the two cases. So here is a summary of the connection. The hypothesis function is the posterior distribution. So you have 1 given x and 0 given x. That will give you the sigmoid function or x sigmoid function of 1 minus h. And then, so logistic regression offers a probabilistic reasoning, which the linear regression doesn't. So that is one advantage of the logistic regression model. I'm not saying that logistic regression is giving you a better fitting or not. I'm just saying that it gives you a probabilistic interpretation. Same as what we have discussed last time. It has a posterior interpretation. This lecture will make it more clear that that connection is true when your underlying distribution is indeed a Gaussian and the two classes, they have the same covariance matrix, then your sigma function is exactly the same as the posterior distribution. Otherwise, you will get something. That something can mean something. It's just not the posterior of a Gaussian distribution.